So the function that described y equals 4, in our example it was 2x, y was 2x1 to the power 1/3, x2 to the power 1/3, and I want it to be 4. That means I can divide this and this and get 2. I can take all of them to the power 3. I'm getting x1 times x2 equal 2 to the 3, 8. x2 equals 8 over, sorry, x1. And when x1 goes to infinity, the x2 is getting close to 0. And when x1 is very close to 0, x2 goes to infinity, when this is close to 0. Okay? So that described that exactly described this isoquant. Okay. I can describe it in a three-dimensional way. I put x1 here, x2 here, and when I go with x2 1 unit and x1 8 units, so 8 and 1, this is the point, I can produce 4 unit of output. If I go x1 equals 8 units, x2 equals 8 units, this is the point 8, 8. How much I can produce? I can produce 8 units, okay? If I put here x1, 8 and 8 to the power 1/3 is 2, 2 and again 2, you get 8 units. So I'm getting that much. So I describe it in a three-dimensional way where the vertical one is the total number of units of output. So this is higher than this, etc., etc. More isoquants tell us more about the technology. If I get all the isoquants, I know exactly the technology. Here, y equals 8, y equals 6, y equals 4, y equals 2, everything on a two-dimensional case, x1 and x2. If I want a third-dimensional case, this will be the lower 2. This will come 4 units up, this will come 6 units, and this will come 8 units. So I can describe it, you see, these are in different scales, each one is higher than the other. This is the vertical output axis. The complete collection of isoquants is the isoquant map. Not that we use this too much, but that's the definition. This isoquant map is equivalent to the production function. Each is the other. You give me production function, this, I can tell you each one. I put here equals 4, equals 6, equals 8, equals to whatever you want. I can find the curve, the isoquant. You give me all the isoquant, I can derive what is the function itself, y equals this. Now let's describe, so here, but now this is the isoquant y equals 8. Maybe here is y equals 7, maybe here 7.5, etc., etc. A lot of isoquants, as you can see. And now I try to put them in a three-dimensional case. So let me go back. You see I have x1, x2, and still the y-axis is hiding. So in order to see it, I move this to the right, okay? And this a little bit down to allow the y to come here as a vertical axis. See now this is the y-axis. x1 and x2. Okay? See, this is 1, 2, so this refers to 2 units of output. This is x2, this is x1, and this is the vertical y. That's it. So as you can see, this is isoquant, and it is represented by the y equals 8. Or in all of them, y equals 8. For your information, it doesn't look here, but if you would project this isoquant, this and this, into the two-dimensional case x1 and x2, you will get whatever we saw before. Okay. A Cobb-Douglas production function is of the form as before, but what we did in utility, we did it only with two commodities. You can have it with n commodities. Y equals a number times x1 to the a1, x2 to the a2, etc., xn to the an. Our example before it was before it was 2 times, but you can get it 1 time. But so let me. I don't think we should write yet anything. So if I take this one, the a is 1. Because the coefficient is 1. A1 is 1/3, A2 is 1/3, and the number of inputs that I have, just 2, x1 and x2. And the isoquants goes like this. Okay, if you want a typical isoquant, it is this. But well, here we talked about y equals x1 to the A1, x2 to the A2, that's it. Okay? Just x1. Yeah. So let's say I want to find out x2. What is isoquant? You fix the y. So fix the y, think of it as a number, 7. And now you get x2 to the A2 equals y over x1 to the A1. Now you take 1 over A2, okay, 1 over A2 on both sides. So that will be x2, and this will be y to the power 1 over A2 divided by x1 A1 over A2. So you get as before, x2 equals x1 to some power, everything is positive, and this is a number. Okay, 7 to, let's say A2 was 2, square root of 7. So you don't care, but it looks exactly, when x1 goes to infinity, it becomes close to 0. So as you can see, when x1 goes to infinity, all of them becomes very close to 0. And then when x1 is very close to 0, you get something, you divide something by a small, very small number close to 0, you get infinity. So they look like this. So you take a specific one, what does it mean? Y equals y double prime. So a very specific one. So this is an all combination of x1, x2, x1, x2, x1, x2, etc. So that x1 to the a1, x2 to the a2 equals y prime. And then I can tell you, it's written here, how x2 relates to x1. Where this is fixed at the level y double prime. And this is another one, y prime. So you fix the level of output to be y prime, some number, let's say this is 4 and this is 9. Okay? And you get again, according to what's written here, another formula of x2 as a function of x1. And each isoquant has it is a function of x2 to x1. Here you say, take the fact that if y double prime is bigger than y prime, then you move from here to here up. So that this isoquant will have y triple prime, which is higher than y double prime, etc., etc. Everything moves in this direction. Okay, that's for the time being related to the Cobb-Douglas. Now I want to talk about a fixed proportion. If you remember, perfect complement. Okay, what does it mean? Minimum of A1, X1, A2, X2 up to AN, Xn, y equals to this. Let's say that all the AIs are 1 for a second. So you get minimum of X1, X2 up to Xn. So that means that I need a unit from each one of them, or 2 units from each one of them. If you give me, let's say that x1 will have 1 unit, and x2 2 units, I cannot do anything with it, because I look on the minimum. So, if you remember, production of coffee, okay? So I want to produce coffee, and let's say this is minimum of x1, x2. This is the number of cup of coffee. And this is the teaspoon of coffee beans, grained, to be just consistent with our previous lectures. This was the sugar, let's say, and this is the teaspoon of sugar, and this is teaspoon of grained coffee bean. Okay, so I just need the minimum of the 2. If you give me this is 1 and this is 3, what I can produce only 1 cup of coffee, because I'm drinking 1 teaspoon of sugar, 1 teaspoon of coffee. So I really need the minimum. So this will be completely waste. It will not be efficient to use 3, and this is 1. The minimum of 1 and 3 is 1. And if you give me the minimum of 5 and 7 is 5. So if you give me 5 teaspoons of sugar, 7 teaspoons of coffee, I can produce 5 cups of coffee. So how it looks like, the L shape. What did I do? So for instance, here A1 can be 2, or A1 is 1 here, x1, and this is 2, 2x2, number of, in this case, I have number of inputs n equals 2, and that's it. It looks like this. So first of all, how do I do it? I remind you, I set x1 equals to x2, or if you like, x2 equals half of x1. So this is x1 equals x2, but if I look on x2 and x1, I like more to write it as x2 equals half of x1. And then, as you can see, if this is 4, the x2 will be half of it. If this is 8, the x2 will be half of it. Okay. So it looks like this. This is the isoquant of producing 4, if you like, 4 cups of coffees. 8 cups of coffees. So if I go here, these are the efficient point. Just when they are equal, I don't want to, because I need the minimum of the 2, I don't want to spare or to waste. So it must be equal. So actually the efficient production will be here, 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 here. This is inefficient because I waste my x1. I just need to add this much of x1 and this much of x2. Why should I put more x2 or more x1? So this is actually the production function. And we move on to a perfect substitute. This was a perfect complement, okay, goods. And this is perfectly substitute, namely linear equation, y equals a1 x1 plus a2 x2 an xn. So an example, y equals x1 plus 3x2, a1 is 1, a2 is 3, and the number of inputs is 2. Let's take x1 plus y equals x1 plus 3x2. And let's take 3 levels of output y. So if y equals 9, it will be this one. Why? Because when x2, so x1 plus 3x2 equals 9, then when x1 equals 0, x2 equals 3, and when x2 equals 0, x1 equals 9. This one is when x1 is 0, x2 is 6, when x2 is 0, x1 is 18, and this one is when x1 equals 0, x2 equals 24 over 3, 8, and 24. So these are all parallel lines, okay, to each other. because the slope of all of them is 1 to 3. Now I'm moving to another concept, very similar to the marginal utility. Now it will be marginal product. Now, so I take the function y equals fx1 up to xn to remind you. This is y is how many units of output I can produce from x1 up to xn units of inputs. So the marginal product of input is the rate of change. I'll come back to explain what I mean by rate. Is the rate of change of the output level as the level of input I changes, holding all other inputs levels fixed. Okay, so first of all, it's a derivative of y to partial derivative of y with respect to xi. But let me explain slowly what does it mean. What do I mean by rate? I want to see how much extra unit units of output I can get per unit change of the input number I. I have n input, so I change input I. Okay? And therefore I want to see by how much I change. I can change it by a lot, by small. Let's do it a small change. So if I change my input from xi to xi plus a little bit, I want to see by how much I change the y. And then I take the ratio between the two. That is the rate. However, that ratio depends by how much, even if it's small, by what is the change of the xi. So in order not to be dependent on the number of units or how small my change in xi is, I take the ratio between the change in output divided by the change in input, where the change in input is extremely very, very small, as the limit. This is exactly the definition of the derivative of f with respect to xi. I don't want to take too much of you, but let me try to explain it to you. What do I do? So I look, instead of looking on f, and I look on x1, and when I get to xi, I put plus some delta. So I take an increment of xi, and I continue xi plus 1. I don't change the others, xn. Just I see what happens if I change only the xi, I put a little bit more. What is the change? So I have to look on the difference between what was before. Before it was fx1 xn, here at some point you have xi, before changing. So now I change xi, just xi, and I take a little bit more, xi plus delta. So this is the change in output. This is the first, this is the change, let me write down here, change of output due to a change of delta units of input I. Can we see it? Now I want to, so this is the change in output. Per unit change of input, I have to divide it by the number of units of input that I change. This is exactly delta. Now, if I put here delta equals 1, and I divide by 2, divide by half, divide by half, I will get different ratios. So what do I take? Well, I do it when the change in the output is extremely small. So I take this, and when delta becomes very small, go to 0, then it will be df to dxi at the point x1 up to xn. So yeah, as you can see, when I divide by delta, I actually make it the change in output per unit change in input. By dividing by the number of units of input that I change, I get a change per unit. Now I take the change per unit and I make it as small as possible, and therefore we call it the rate of change. Okay? So this is, it's a derivative, partial derivative, but if you want to think of it intuitively, what happens if I increase by a unit, small unit, the amount of a certain input, per that change, okay, per unit change, what is the change in the output, or per unit change in output? It's called the rate, but that's a definition. You sure that the most important thing is to understand also, but to be able to apply that. So actually the MPI, the marginal product, is the derivative of y with respect to xi, or if you like, the partial derivative of f to dxi. So this you can also, it is the same as to write like this, dy to dxi. Why? Because f of this is y. So all this is the y. Let's see examples. Suppose that y equals f x1, x2, Cook-Douglas with 1/3 and 2/3. Now let's see what about the marginal product that we get.